Okay, guys, we are going to dive into Chapter 9. Chapter 9 is on correlation and regression and is our second to last chapter for the semester. So Section 9.1, Scatter Diagrams and Linear Correlation. Focus points: make a scatter diagram visually, estimate the location of the best fitting line for a scatter diagram. Eventually, you will see that best fit does not always have to be linear. Sometimes it can be quadratic, sometimes it can be cubic. Use sample data to compute the sample correlation coefficient R. Investigate the meaning of the correlation coefficient R. All right, studies of correlation and regression of two variables usually begin with a graph of paired data values x and y. We call such a graph a scatter diagram. A scatter diagram is a graph in which data points x and y are plotted as individual points on a grid with a horizontal x-axis and a vertical y-axis. We call the x the explanatory variable and y the response variable. By looking at the scatter diagram of point data pairs, you can observe whether there seems to be linear relationships between x and y values. Phosphorus is a chemical used in many household and industrial cleaning components. Unfortunately, phosphorus tends to find a way into its surface water where it can kill fish, plants, and other wetland creatures. Phosphorus reduction programs are required by law and are monitored by the Environmental Protection Agency, the EPA. A random sample of 8 sites in California wetlands study gave the following information about phosphorus reduction in drainage water. In this study, X is a random variable that represents phosphorus concentration in 100 milligrams per liter at the inlet of a passive biotreatment facility, and Y is the random variable that represents the total phosphorus concentration in 100 milligrams per liter at the outlet of the passive biotreatment facility. So we're going to make a scatter diagram for this data. They give it to you here. And figure 9.1 shows the points corresponding to the given data pairs. So you can see here it's extremely linear. Unfortunately, that also should tell us that we have an increase in phosphorus. These plotted points constitute the scattergram. To make the diagram, first scan the data and decide on an appropriate scale for each axis. Figure 9.1 shows the scattered diagram points along with a line segment showing the basic trend. Notice a jump scale on both axes. That's when you use the squiggly line. Interpretation. Comment on the relationship between x and y shown in figure 9.1. By inspecting the figure, we see that the smaller values of x are associated with smaller values of y, and larger values of x tend to be associated with larger values of y. Here you can see that on the low end, we're both low, and then it just continues. Roughly speaking, the general trend seems to be reasonably well represented by an upward sloping line segment as shown in figure 9.1. We can draw many lines in figure 9.1, but in some sense, the best line should be the one that comes closest to each of the points in the scatter diagram. To single out one line as the best fitting line, we must find a mathematical criterion for this line and a formula representing the line. Another problem precedes that of finding the best fitting line. That is the problem of determining how well the points of the scatter diagram are suited for fitting any line. Certainly, if the points are very poor fit to any line, there is a little use in trying to find the best fit line. If the points of a scattergram are located so that no line is realistically a good fit, we say that the points possess no linear correlation. We see some examples of scatter diagrams for which there is no linear correlation in 9.2. Here we would have a quadratic, and here there would just be nothing. That's a bit of a wild card there. If the points seem close to a straight line, we say the correlation is linear, moderate to high, depending upon how close the points lie on the line. If all the points do in fact lie on a line, then we have a perfect linear correlation. So in figure 9.4, we see that in C and D, but a moderate linear correlation in A and B. All right. In statistical applications, perfect line correlation almost never occurs. The variables x and y are said to have positive correlation if low values are associated with low values and high are associated with high. A and C show scattergrams in which the variables are positively correlated. On the other hand, if low variables are associated with high values of y and vice versa, then they are negatively correlated. So here in 9.4, parts B and D, they show negative correlations. All right, sample correlation coefficient R. Looking at the scatter diagram to see whether a line of best fit describes the relationship between the values of data pairs is useful. In fact, whenever you are looking for a relationship between two variables, making a scatter diagram is a good first step. There is a mathematical measurement that describes the strength of the linear relationship between two variables. This measurement is the sample correlation coefficient, R. The full name for R is the Pearson product moment correlation coefficient, named in honor of the English statistician Karl Pearson, who is credited with formulating R. Here is your procedure, I guess is what they've been calling it, the whole textbook. I will give you a moment to pause and write that down. All right, development of the formula for R. If there's a positive linear relationship between variables x and y, then high values of x are paired with high values of y, and low values of x are paired with low values of y. So again, see the figure. Low and low, high and high, and this would be positive. For negative, low and high, and high and low, again for negative. If there's little or no linear correlation between x and y, however, we will then find both high and low values, sometimes paired with the opposites. You can see here low and high, high and high, low and low, high and low. You don't really have any idea of what's going on here. These observations lead us to develop the formula for the sample correlation coefficient R. Taking high to mean above the mean, we can express the relationships pictured in figure 9.6 by considering the products. X minus X bar times Y minus Y bar. If both X and Y are high, both factors will be positive, and the product will be positive as well. The sign for this product will depend on the relative values of X and Y compared with their respective means. The product will be positive if X and Y are both high. It'll also be positive if X and Y are both low. It'll be negative if X is low but Y is high. It'll also be negative if X is high but Y is low. I think from your basic algebra, you guys would all know this. In the case of positive linear correlation, most of the products will be positive, and so the sum over all the data pairs. And so will the sum, okay? For negative linear correlation, the products will tend to be negative, so the sum will also be negative. On the other hand, in the case of little, if any, linear correlation, the sum will tend to be 0. So that is a little internal check you can run. One trouble with the preceding sum is that it increases or decreases depending on the units of x and y. Because we want R to be unitless, we standardize both x and y of a data pair by dividing each factor by the sample standard deviation and each y factor by the y version. Finally, we take the average of all the products. For technical reasons, we take the average by dividing by n minus 1 instead of by n. This process leads us to the desired measurement R. So here is the entire formula. They kind of gave you a step-by-step proofing of it. All right, computation formula for R. What? Give me a second. Hold on, guys. Okay, so unfortunately the computation formula for R procedure and then the interpretation slides are not available. I've tried switching it to my other screen. It's not the screen issue. I've tried refreshing. It's just an issue with their PDF, with their PowerPoint. I've also checked the PDF and it's wrong on there as well. So you will have to refer to the textbook for these ones. I do apologize for that. All right, computation formula for R. If R is between 0 and 1, then you have this set up. If it's between -1 and 0, you have that set up. Go ahead and read those for yourselves. All right. Here's our example. Sand driven by wind creates large, beautiful dunes at the Great Sand Dunes National Monument in Colorado. Of course, the same natural forces also create large dunes in the Great Sahara and Arabia. Is there a linear correlation between the wind velocity and sand drift rate? Let x be the random variable representing the wind velocity in 10 centimeters per second, and let y be the random variable representing drift rate of sand in 100 grams per centimeter per second. Remember, R is unitless, so that won't really affect you. Test site at the Grand Sand Dunes National Monument gave the following information. Here they give you a reference. Here's the data. We would just plot it. Construct a scattergram. Do you expect R to be positive? So figure 9.7 displays the scattergram. From the scattergram, it appears that X values increase and Y also tends to increase. Therefore, R should be positive. So here it is. And you can see it's moderately linear. Guess it's not really exponential. Compute R using the formula. Again, they had given it to you, so you find all of these things first. It is convenient to organize the data in a table of 5 columns. So here you go. If you follow this, you will be able to keep things nice and organized while you do your homework, quizzes, and exam. And then the sum of the entries in each column. Of course, many calculators give these sums directly using the computation formula for R. The sums from table 9.3 and n equal to 7, we have the following. And here they're working it all out for you. So R is positive and it's about 0.949. I would recommend working this problem out before you go to your homework, but that is up to you. Note, using a calculator to compute R directly gives you 0.949 to 3 places after the decimal. Interpretation, what does the value of R tell you? Since R is very close to 1, we have an indication of a strong positive linear correlation between wind velocity and drift rate of the sand. In other words, we expect the higher wind speeds tend to mean greater drift rates because R is so close to 1, the association between the variables appears to be linear. Because it is quite a task to compute R for even 7 data pairs, the use of the columns as an example 2 is extremely helpful. Your value for R should always be between -1 and 1 inclusively. So again, if you mess that up, you will be able to know. Use a scattergram to get a rough idea of the value of R. If your computed value of R is outside the allowable range, or if it disagrees quite a bit with the scattergram, recheck your calculations. Most softwares that you can make a scattergram with will have an option where you can display your R value. At this point, I know you all know how to calculate things, so I'm perfectly fine if you do that. Be sure you distinguish between expressions such as the summation of x squared and the summation of x squared. What? Negligible rounding errors may occur depending upon how you or your calculator round them. I'm not sure what they're trying to say here, unless they were trying to say like the sum of the x squareds versus the sum of, like, you add all of the x's and then square the sum. Like, those are the same thing right there. I don't know what they're trying to say. Obviously, you guys know the difference between summing the x's and squaring it versus summing the x squareds. The only thing I can think they were trying to say here is that this is different than this, which that is true. But what they gave you there, that is the same exact things. All right. Okay. Section 9.2, linear regression and the coefficient of determination. Again, here are your focus points. You can take a moment to pause and write them down if you are someone who is a note taker. Again, here's the second set of focus points. We're going to cover them all. In Denali National Park, Alaska, the wolf population is dependent on a large, strong caribou population. In this wild setting, caribou are found in very large herds. The well-being of an entire caribou herd is not threatened by wolves. In fact, it is thought that the wolves keep caribou herds strong by helping prevent overpopulation. Can the caribou population be used to predict the size of the wolf population? Let X be a random variable that represents the fall caribou population in the hundreds in Denali National Park, and let Y be the random variable that represents the late winter wolf population in the park. A random sample of recent years gave the following information. Again, you can see that they gave reference to their source. And again, they made a scattergram. So now that they have this, they can ask some questions. Does the data indicate a linear relationship between X and Y? Can you find an equation for the best fitting line relating X and Y? Can you use this relationship to predict the size of the wolf population when you know the size of the caribou population? And what fractional part of the variability in Y can be associated with the variability in X? What fractional part of the variability in Y is not associated with a corresponding variability in X? The first step in answering these questions is to try to express the relationship as a mathematical equation. There are many possible equations, but the simplest and most widely used is the linear equation, or the equation of the straight line. Because we will be using this line to predict the y values from the x values, we call the explanatory variable and explanatory variable the x and y the response variable. Our job is to find the linear equation that best represents the points on the scattergram. For our criterion, our best fitting line, we use the least squares criterion, which states that the line we fit to the data points must be such that the sum of the squares of the vertical distances from the points to the line be made as small as possible. The least squares criterion is illustrated in 9.10. So here you see the distance there is really, really small. All right. The least squares criterion. The sum of the squares of the vertical distances from the data points x and y to the line is made as small as possible. In figure 9.10, D represents the difference between the y coordinate of the data point and the corresponding y coordinate of line. Thus, if the point lies above the line, D is positive, but if the data point is below the line, D is negative. As a result, the sum of the D values can be small, even if the points are widely spread in the scattergram. However, the squares D squared cannot be negative. By minimizing the sum of the squares, we are in fact not allowing positive and negative D values to cancel out one another in the sum. It is this way that we can meet the least squares criterion of minimizing the sum of squares of the vertical distances between the points and the line over all points in the scattergram. We use the notation y hat equal to a plus bx for the least squares line. A little algebra tells us that b is the slope and a is the intercept of the line. In this context, y hat represents the value of the response variable y estimated using the least squares line and a given value of the explanatory variable x. Techniques of calculus can be applied to show that a and b may be computed using the following procedure. Sorry, guys. I did not take my allergy pill today, and it is kicking my butt. Go ahead and pause this here so you can write down your procedure. Let's find the least squares equation relating to the variables x equal to the size of caribou population in hundreds and x equal to the size of wolf population in Denali Park. I believe this second x is a typo and it's supposed to be a y. Use x as the explanatory variable and y as the response variable. Use the computation formulas to find the slope b of the least squares line and the y-intercept a. Table 9-7 gives the values of x and y along with the values x squared, y squared, and x times y. Again, they're using their 5-column method. I definitely recommend this table. All right, first compute the sample means. So x bar, about 25.14, y bar, 62.5. Now we can use the information from the table to find slope. So there they have it. Again, I would totally recommend going through these problem sets before you do your homework. All right. Use the values of b, x, and y to compute the y-intercept a. Note that the calculations give the values b equal to roughly 1.599 and a equal to 22.36. These values differ slightly from those computed using the formulas because of rounding. Okay, use the formulas of a and b, either computed or obtained from a calculator, to find the equation of the least squares line. So y hat is going to equal 22.35 plus 1.60x, since a is about 22.35 and b is about 1.60. You could have used either. Those little rounding issues may get you in trouble on WebAssign. If they do, if you think you have a rounding issue, just email me and I will let you know if you're super off or if you're close enough that I can just give you credit. Graph the equation of the least squares line on the scattergram. To graph the least squares line, we have several options available. The slope-intercept method of algebra is probably the quickest, but may not always be convenient in the intercept if the intercept is not within the range of the sample data values. It is just as easy to select two x values in the range of the x data values and then use the least squares line to compute two corresponding values. In fact, we already have the coordinates of 1 point on the least squares line, but the formula for the intercept, the point is always on the least squares line. For example, xy 25.14, 62.57 is always on the least squared line. Another x value within the range is 34. Using the least squared to find the y value gives 76.75. Okay, so now we have these 2 points on the line, and they do fit right on that line. In each equation, the slope b tells how many units change for how many for each y hat in x. In example 4, regarding size of wolf and caribou populations, the slope tells us that if the number of caribou in hundreds changes by 1 or 100, then we expect the sustainable wolf population to change by 1.6. In other words, our model says that an increase of 100 caribou will increase the predicted wolf population by 1.6. If the caribou population decreases by 400, we predict the sustainable wolf population to decrease by 6.4. The slope of the least squares line tells us how many units the response variable is expected to change for each unit and the explanatory variable. The number of units change and the response variable for each unit change in the explanatory variable is called the marginal change of the response variable. Some points in the data set have a strong influence on the equation of the least squares line. A data pair is influential if removing it would be substantial change the equation of the least squares line or other calculations associated with linear regression. An influential point that has an x value near the extreme high or low of the data set. So 9.2 shows 2 scattergrams produced in Excel. 912A has an influential point. You can see it right up there. whereas 912b shows a scattergram with the influential point removed. Notice that the equation for the least squared lines are quite different. So let me back up and show you that again. So here's one with the point included, and you can see your y hat would be 3.47x minus 6.33. And then when you remove it, you have a y hat of 1.45x plus 1.75. If a data set has an influential point, look at the influential point carefully to make sure it is not the result of a data collection error or a data recording error. A valid influential point affects the equation of the least squared line. The group project in data highlights at the end of this chapter further explores influential points. Coefficient of determination. There is another way to answer the question, how good is the least squared line as an instrument of regression? The coefficient of determination, r squared, is the square of the sample correlation coefficient r. Suppose we have a scattergram and corresponding least squared line as shown in figure 914. Okay, and I'll give you time to pause this so you can take this diagram down. Let us take a moment. Let us take the point of view that y bar is a kind of baseline for the y values. If we were given an x value and we were completely ignorant of regression and correlation, but we wanted to predict a value of y corresponding to a given x, a reasonable guess for y would be the mean y bar. However, since we do not know the construct of the least squares regression line, we can calculate y hat equal to be a plus bx, the predicted value corresponding to x. In most cases, the predicted value of the least squares line will not be the same as the actual data value y. We will measure deviations or differences from the baseline y bar. Total deviation, y minus y bar. Explained deviation, y bar minus, or y hat minus y bar. Unexplained deviation, y minus y hat, also known as the residual. The total deviation, y minus y hat, is a measure of how far y is from the baseline y bar. This can be broken into two parts. The explained deviation tells us how far the estimated y value should be from the baseline y hat. The explanation of this part of the deviation is the least squares line, so to speak. The unexplained deviation tells us how far our data value of y is off. The amount is called unexplained because it is due to the random chance and other factors that the least squares line cannot account for. So if you take a look, we have our total deviation equal to our explained deviation plus our unexplained deviation. At this point, we wish to include that all data pairs, and we wish to deal with only one non-negative value so that positive and negative deviations won't be canceled out. Therefore, we construct the following equation for the sum of squares. This equation can be derived using some lengthy algebraic manipulations, which have been omitted in the PowerPoint, thankfully. Okay, so again, total deviation summed and squared, explained deviation summed and squared, and then unexplained deviation summed and squared. Note that the sum of squares is taken over all data points and is then referred to as variation, not deviation. The preceding concepts are connected together in the following important statement, whose proof we have omitted. Okay, so here's your little statement that you want to be aware of. Let us summarize our discussion. Again, you guys can take a moment and write that down for yourselves. Oh. Okay. In other words, the coefficient of determination r squared is a measure of the proportion of variation in y that is explained by the regression line using x as the explanatory variable, r equal to 0.9 and r squared equal to 0.81 is the coefficient of determination. We can say that about 81% of the variation behavior of y variable can be explained by corresponding variation behavior of the x variable if we use the equation of the least squared line. The remaining 19% of the variation behavior of the y variable is due to random chance or the possibility of lurking variables that influence y. Okay. All right. That is it for the first half of chapter 9. I will record the second half and post it later. All right. If you guys have any questions, please make sure that you email me. And I look forward to seeing all of your career projects.